Okay, so once again, I have a quantum mechanics exam in about 10 days, so I'm going through and doing problems out of Griffiths quantum mechanics textbook. I'm going to do more videos like this in the coming days, so if you enjoy this, please like and subscribe. Okay, so problem 6.3. Show that the operator p hat prime obtained by applying a translation to the operator p hat is p prime equals t dagger p t equals p. In other words, we want to show that momentum is invariant under this translation. Okay, so we'll start with just the equation. Okay, so that's just our equation. That's 6.6 in Griffiths quantum mechanics textbook. Now I'm going to multiply both sides by f of x, and f of x is just a test function. And this is just to help me keep myself straight. So these are just test functions. At the end of this, I'm going to divide the f of x out, so it's as if it never existed, but it helps me with bookkeeping. So I'm going to do that. Okay, so let's start with this. This is really and then this would be of a translation A. Okay. So our translation operator is doing it by a unit A. And what we need to know about the translation operator is that it is e to the minus I a p hat over h bar. So if we wanted to take a complex conjugate, and this is for A, of course, I should specify. So T dagger is E to the I A p hat over h bar, changing the sign on our I. And this is just T of minus A. So we can represent T dagger then as simply T of minus A. So that's what I'm going to do. Well, also, we know what p hat is. P hat is minus I h bar d by dx. So I'm going to go ahead and substitute that in here. And the other thing to mention is that a translation operator acting on a function, all that does is that shifts it to f of x minus a. So this becomes just f of x minus a when this operates on it. And then this is our p. Okay. So now that we have that, one thing you can check for this if you don't believe me, but T and P commute. What that means is T operating on P is equal to P operating on T. And this really makes sense if we look at how we define our T. T has momentum in it. So surely the momentum operator is going to commute with itself. I bring that up because I'm going to rewrite this. I'm going to switch these two. And we can do that because these commute. If these didn't commute, then you have to be a lot more careful because these are operators. They're not numbers. So we do have to be careful with the order. But because they commute, we can actually be a little more carefree. So we have p prime f of x equals, I'm just going to call it p hat. I just wanted to show that it was the derivative. It's an operator. We can see that here. It's actually not that important because it commutes, but it's fine. And when we have this operator, we're going to subtract whatever's in the argument. So this is f of x minus a minus negative a. So of course, this is just equal to f of x. And as I promised in the beginning, we can divide out by this test function. Again, it was just there to kind of keep ourselves straight with what was happening, not actually needed. And we see that p prime is equal to p, which is what the question asked for. So hopefully that makes sense. If you'd like more solutions for Griffiths quantum mechanics textbook, please like and subscribe.